Right, so now we'll start chapter 3, and we'll move on to slightly more advanced topic of open sets. Now, you're probably beginning to get an intuitive notion of open sets and closed sets already, because we've been describing certain sets using the words open and closed already. But we don't have a definition of what we really mean by open or closed. You know now, if you're given some sort of interval or D-cell or something like that, what it means to be open, because you're going to be excluding all the points on the boundary, and closed because you're going to be including all the points on the boundary. But actually, we don't have a proper definition of boundary, and we don't have a proper definition of open, we don't have a proper definition of closed, and most sets aren't as nice as that. Suppose you've got the rational numbers in the reals. What on earth is the boundary of that set? Actually, we'll come up with an answer for that, but let's not worry about it for the moment. If you take the rational numbers, as just all these dots everywhere in the real numbers, it's a bit tricky to figure out what the boundary of that might be. So it's rather difficult to decide whether it includes or excludes its boundary. And in fact, the answer is neither. It's got some of its boundary in, but not all. So, and because it's not an interval, you won't be using the term half open. So the rational numbers will just be a relatively nasty set in the reals. One of the nastier sets that we'll meet in this module. Of course, by the time you get to third year, the rational numbers is a really nice set compared to some of the other nasty sets you're going to meet. But for second year, the rational numbers is allowed to be a nasty set. Right, so we're going then to decide which kind of sets do we think are nice, what's our official definition of open going to be. Whatever our official definition of open is going to be, it had better work for the sets that we've already called open. Which is why, a bit later in this chapter, we're going to prove that open balls are open. Which sounds completely stupid, but we don't have a definition of open yet. Now I'm going to give you a definition of open in a moment. Once I've given you a definition of open, it had better work for the sets that we've already been calling open. Otherwise, we shouldn't have been calling them open in the first place. What do we need? We need to know our notion of distance, and we already know that. Our notion of distance is using Euclidean norm. But if you go into like a third-year module on metric and topological spaces, then you'll see lots of other notions of distance there. Every notion of distance comes with its own notion of open ball and closed ball, and from that it comes with its own notion of open set. And if you change the notion of distance, you might change the notion of open set. Though sometimes, even changing the distance might leave you with the same sets being open or closed. That's something you'll find out all about in the third-year module, metric and topological spaces. Again, the advantage of what we're doing is that although we'll often draw two-dimensional or three-dimensional pictures, or even one-dimensional pictures, most of what we say will work in D dimensions as well, even though it's hard to draw the pictures there. But the arguments will often be completely general arguments that just use properties of the distance. And if you only use properties of the distance, which we know happen to hold in D dimensions, like the triangle law, then you're safe, because your proof works in D dimensions as well. If your argument is based entirely on a picture with no backup from something like the triangle law, then you don't know that your picture is valid in D dimensions. So as I say, here's an advert for the third-year module, metric and topological spaces. That module is much more abstract than this one, and it's harder than this one. So, and it's got, you even need to be more ingenious in that module than this one about being able to prove things for yourself. You need, to do the third-year module on metric and topological spaces, you should feel confident about proof, I would suggest, before you commit yourself to that one. If you're worried about proof, that's not a good module to choose. This should be the module you use to help you get happier about proofs. And if you decide you do like proofs after all, and you like this whole area, then the third-year module on analysis may be the right ones for you. So we're going to start, and I should say different authors do this in different ways. So if you look in different books, you'll find different approaches to how to define open, and so on. And I invented for myself a concept that doesn't have a name in the literature, the notion of non-interior points in a set. And you may wonder, why am I giving you a concept and a notation that isn't in the literature? And the reason is that I found that it helps people to understand what's going on in the past. And I'll leave it to you to decide whether you find it helped you. But I certainly find it's helped a lot of people to understand this particular concept. And for some comments on that, you can have a look on my maths blog. By the way, I've got a blog called Explaining Mathematics, which is worth looking at. It tells you about some of my ideas about how to try to explain some of these concepts that students do find hard. And there's a link to that from most of my module web pages. Right, so we're going to distinguish two different kinds of point in a set. So obviously you've got a set, you've got points in the set, and you've got points outside the set. When you look at the points inside the set, I'm going to classify them as two different kinds. Those points that are in the interior of the set, and those points of the set which are not in the interior of the set, which will of course mean they're somehow at its edge or at its frontier or something like that. In a way we're going to make formal now. Now, one way to avoid, suppose you take a ball, like an open ball, one way to avoid being at the edge of the ball is to be right at the centre. But of course you don't have to be right at the centre really to avoid being at the edge, but that's where we start. So you start by thinking about a point at the centre of an open ball. So here's the open set, the open ball, I should say, B little r of A. This is where A is some point in R to the D, and little r is a positive real number. And I just write little r greater than 0 as usual. Well, obviously, if you start from the centre and you go a little bit in any direction, you're not going to leave the ball. You're still going to look at points inside the ball. But that's true for some other points as well. If I take another point, say halfway towards the edge of the ball, there's still quite a lot of room to move in here. So if I take another point B, you can see there's still quite a lot of room to move in any direction round B. As long as I haven't gone right to the edge, I'm still going to say inside the same ball centred on A. So there's still room to move round B as well. Without leaving that open ball centred on A. So if you've got a point of a set, and you can move a little bit in every direction without leaving the set, I'm going to say you're an interior point of that set. But now suppose you were right at the edge of the set, then it wouldn't be true anymore. If you're right at the edge of the set, then there's going to be some direction at least you can move in where you actually end up leaving the set. So now you take a general set, and this could be a pretty horrible set, as you know, but for the purposes of the drawings I'm going to do, I'm going to assume they're reasonable shapes in 2 dimensions to draw the pictures. But the fact of the matter is they could be pretty horrible sets like the rational numbers, in which case you've got to figure out what these definitions mean. So the points of the set will be classified as interior points of S or non-interior points in S. In the following way. Note that you must be in S to do this classification. They're actually interior points. Interior point is a bit easier for reasons we'll see, but non-interior point, it's rather important what our definition is. And it's a non-interior point is the non-standard terminology which I've invented. So you're an interior point if, informally, there's a little bit of room to move in every direction without leaving the set. So how do you formalize that? That means that you should be at the center of some ball that's entirely contained in the set S. So there has to be some positive real number R so that if you move less than R in any direction, you stay inside S. That's what's going on there. And if that isn't true, you're a non-interior point in S. And so we've got the standard notion of the set of all interior points of S called the interior of S. This is standard, and I normally use this notation int S. But some people use this notation S with a little circle over the top. The non-standard notation is this non-interior, where I use nint S. And I would never dream of writing it, but the opposite of the interior is the ninterior. Nobody talks about that. So no other lecturers will know what you're talking about if you write nint S, except possibly those people I've talked to about this concept. So this is special for this module. It's just a way of saying it's a point of the set which is not an interior, and not in the interior. So the ninterior of S is what you get by taking away from S the interior of S. Let's draw a little picture to say a little bit more about what's going on. For this picture, I'll assume that the set actually includes its boundary, just to make life a bit easier. So here's your set S. And I point out here, so let's put a point out here, A. If A is not an element of S, so A is not in interior of S, and A is not in the interior either. Because the interior and the ninterior only about points in S. Now, let me draw a point that is in S and is right in the interior of it. So here, X is in the interior, with or without brackets of S. I don't mind whether you put those extra brackets in or not. If the set has got a more complicated definition, it can be safer to put the brackets in. And then, if I take a point that's in S and at the edge of S, like this, then as you see, no matter what ball I try here, there's going to be some points outside. So here's a point at the edge. Here, let me make that a bit bigger. Try again. Okay, so that too much has gone there. Let's just try again. I want Y. So Y is in S but at the edge of S. No matter what size ball I try and put around Y, it's going to have some points outside Y in it. Maybe some points inside Y as well, of course, Y itself. But Y, so here, Y is in S, but Y is not in the interior of S. So Y is in the interior. y the non-interior point that's in S. Okay. So that's three different kinds of points. Points that aren't in S at all, points that are in S, but not in the interior of S. So that's the non-interior points in S. And then there's the points that are right inside S and not at the edge. And that's the interior points. So interior point and interior standard. But non-interior point in S and nint S are non-standard, and so you have to watch out for that. So if you use that in some other module, you're going to have to tell the lecturer what you're doing. Non-interior points in S have to be in S. I've said that already, and I already drew that in the previous picture. So I won't have to draw that again. So that I can just say, see the previous picture, they must be in S. So now we know which points are in the interior and which points are not in the interior for two different reasons. There are two ways to not be in the interior. One is to be a non-interior point in S, so to be in nint, and the other is to be completely outside the set. I mean, just not a point of S. That's two ways, so two different ways to avoid being in the interior. So what does it mean to be a non-interior point? It means that you're not an interior point. So let me just say how this works. And this is where you start to get a bit of practice in using quantifiers and negation and so on. And this is something you may not have done very often since first year, or indeed not that often in first year. So let x be a point of S. I'll just remind you what it means to be in the interior. So in the whole of this bit about let x being in S, that's going to hold throughout the following. That's going to still be true when I get to negating this statement. So let x is in the interior of S if and only if there exists an R greater than 0 such that the ball radius R centered on X is contained in S. So if I want to know what it is to be in nint S, so again, given x is in S for this bit, this is a standard exercise in negation, and I'll show you what I mean by a standard exercise in negation. X is in nint S if and only if it's not true. Here's a symbol for not. There's two different ways to write not. So it should not be true that there exists an R greater than 0 such that the ball radius R centered on X is contained in S. Now, that's not very satisfactory. It's just saying something doesn't hold. Well, there's a standard technique if you want to say not there exists, that's the same as for all R, something is false. So not turns exist into for all, and then the rest, you get rid of the such that, and it has to be for all R greater than naught, we have it's not true that the ball radius R centres on X is contained in S. By the way, this word contained is quite dangerous as well. Perhaps is a subset of S may be safer, so you don't get confused between subset and element. And that's if and only if, for all R greater than naught, we have the ball centres on X, radius R, is not a subset of S. However, that's still not very satisfactory. What does it mean to say a set is not contained in another set? It means there must be at least one point in the first set that isn't in the second set. So, although this is already correct, I'll go a bit further to give you something that might be easier to use. For all R greater than naught, there is, can be done with there exists, at least one point of the first set which is not in S, which you could write in the following way: if and only if for all R greater than naught, there exists a Y with norm of Y minus X smaller than R, and yet Y not in S. And that's what it means to be a non-interior point of S. This is on the assumption that you're in S in the first place. So, again, there are two ways to be a non-interior point. You can be in S, and this happens, or you can be outside S in the first place. This one won't hold. If you're well away from S, this isn't going to work at all. If you're on the edge of S but not in S, this one does still work, but it doesn't count for being in NINT. And we'll stop there for today.